Right, so with the help of a bit of writing tablet technology today, we'll have a look at geometric isomerism in alkenes. As usual, there might be a few times where you need to pause the video just to catch up with the notes before because you might not have finished writing before we move on. But we'll start with a look at those structures you've got at the bottom there then. Now, there are only two different names there as far as we're concerned so far. The point is that actually by the end of today's lesson, we'll be able to name all four of these distinctly. So let's start with the two on the left here. They're both butene, aren't they? Right? Look at this. Butene. If you look at it, 4 carbons in a chain, double bond in the middle, butene. However, as we'll see, this one we could classify as E-butene. So we'd put a little capital letter E in brackets before. Whereas this one here, we could classify as being Z-butene. Now, clearly, we need to work out what's going on here then. What's this E and Z about? But that's the idea for today. Similar story here then. So when you look at that carbon skeleton, you've got 5 carbons in a chain. Fine. So it's pentene. Numbering from this end, we'll keep from the right hand end there. We'll keep the numbers as low as possible. So it's pentuene. And so each of these structures on the right hand side here is going to be 2-chloro pentuene. Now, following the logic, not that I actually gave you any logic, but following the one example you've got with that pair of alkenes there, the butenes, one's E and one's Z, I wonder if you can use any deduction at all to try and decide which of those is the E and which is the Z. Obviously, the main point of our lesson today is to give you the method for working this out. Well, I'm not going to give you any time to think about that. Pause if you genuinely want more time. But I'm going to say, and again, just listen to this, and I'm going to explain this properly later, but here's my reasoning. Right, this carbon-to-carbon double bond carbon has got a H on it and a C. And the carbon has got more protons in its nucleus than the hydrogen does, i.e. the carbon's got a greater atomic number than the H. So I'm just going to mark that up with a little dot for now and secretly think what I'm thinking. The other carbon in the double bond has got a C and a Cl attached to it. Yeah, that C is part of a CH3, but either way, it's a carbon bonded to the C and also a Cl. And again, in terms of atomic number, Cl beats carbon. So I'm going to put a little mark there as well. And then I'll say, right, so that's got like dot, and then it's this kind of zigzag pattern, right? Rather than that kind of pattern. And so I'm going to have to say that this is the E isomer. Now, let's work through this, and the other one therefore just must be the Z isomer. Let's work through what on earth is going on here. Let me give you a lot more clarity on what's just happened, okay? But there's a working out to it, and you're going to be able to do this kind of working out after this short lesson. So here we go. Now we're going to backtrack just a little bit first of all, because I want to fit this into the context of all of the different types of isomerism that you've studied so far. So again, why don't you, anytime I ask one of these rhetorical questions, why don't you pause and answer it for yourself if you need more time before listening to what I've got to say. So what are isomers? Well, you've met isomers before, you've met structural, branch chain, etc. Isomerism. We need to tidy this up a bit today. They're molecules that have got the same molecular formula, right? So isomers of a given formula, basically, but different arrangements in space, different structures, essentially. So the types of isomerism that you've already met, well, let's have a look at these two here first. We haven't done much with aldehydes yet, apart from look at a few and name a couple, if I remember correctly. But that structure on the left there, as it's labelled, is ethanal. The structure on the right is an alkene, as you can see. It's also an alcohol. That's ethenol, as opposed to ethanol. They're both isomers of C2H4O, aren't they? In this case, we've got functional group isomerism. Same molecular formula, different functional group. It's a pretty dramatic difference. One can undergo addition reactions and also is an alcohol. One can do other sorts of reactions that aldehydes can do that we'll study in the future. But they're clearly isomers of each other, same molecular formula, different structure. So let's make sure that we're really clear on how this all fits together. Isomerism in general is just that idea of same molecular formula, different something. If we're going to subcategorize, then we'll put structural isomerism, that's the types that you've looked at already, as one separate category to what we're going to look at today. So structural isomerism is like a blanket heading, like a banner heading for all those other types that you've already seen. Chain isomerism, so you've got pent, you've got like five in a row, or you've got four in a row with a branch. So that's a branch chain isomerism. You know about position isomerism. Is it 2-chloro? Is it 3-chloro? That kind of thing. Functional group isomerism is a pretty significant difference chemically between chemical 1 and chemical 2, or isomer 1 and isomer 2, I should really say. But those are all types of structural isomerism. What we're going to look at today is a little bit more subtle than that. We won't be seeing optical isomerism for a little while longer because we've got some other functional groups to study before it's sensible to look at optical isomerism. But EZ isomerism, also known as geometric isomerism, that's the sort we're going to be talking about today. Okay, so a little bit more on this. Now, I just want to say a couple more things about structural isomerism, distinct from geometric, or rather just in general stereo isomerism. So you can see that structural and stereo isomerism are like subcategories of the general idea of isomerism here, of having isomers. Within that, you've then got the specific types, chain position functional group on the one side, and here with stereo isomerism, this is where our geometric, also known as EZ, comes in, and also optical for the future. So structural isomerism, branch chain, functional group, or position are where they've got, as always, for isomers, the same molecular formula. But, whoops, I've just realised there's a typo there. But different, that's not supposed to have been missed out. But different structural formulae. So when you can write it on a line, it's going to look different, isn't it? So chain isomerism, let's write the molecular formula for both of these is, well, it's a saturated 4-carbon alkane. So it's N2N+2, so it's C4H10. Both of those, but their structural formulae are different, aren't they? This one's CH3, CH2, CH2, CH3. And the other one is, different. And that's the point, really. CH3, CH brackets CH3 for the one that's coming off the side, CH3. Same molecular formula, different structural formula. We won't do that same thing for all of them because you can see it's going to get pretty messy on the slide. But position isomers you know about, there you'd have this one here, this 2-bromobutane, CH3, CHBr, CH2, CH3, and there CH3, CH2, CH2, CH2Br, because they're different again. And as we've already seen as well, functional group isomerism. Let's just write the formulae for these. Now again, this one here is a functional group you haven't seen very much of so far, and you will quite soon. That's propanone. It's a ketone. It's got a carbon double bond O in the middle of the chain. We'd write that one as CH3CO, CH3. You can see there that the implication, if you misread that, would be that the O is like a bridge between the two carbons in the chain. But if that was the case, this carbon wouldn't have enough bonds when you try to draw a structure like that. So that CO indicates carbonyl, C double bond O. This one we write slightly differently. CH3, CH2, CH, because there is a H on that last carbon, O. Right, and that's called an aldehyde, that's propanal. Anyway, clearly each pair there has the same molecular formula in the pair, but then different structural formulae. Simple as that. And it's kind of obvious, I hope, that because they've got the same structural formula, they must also have different. Because they have different structural formulae, they must also have different skeletal formulae and generally different structures in general. Okay, so now we're on to something new, stereoisomerism then. So as we said, this is a more subtle form of isomerism. We're talking about pairs or groups of molecules that do have the same molecular formula as each other. But actually, if we were to draw the structural formula, the CH3CH2 style formula, you wouldn't see the difference. So it's only when you expand the structure out to like a display formula style or a skeletal formula style, an accurate one at that, or if you build a model of it, it's only then that you see the difference, because they even have the same structural formula. So the difference is quite subtle then, it must be. It's not as obvious as moving a Br one carbon along the chain or branching it. Okay, fine. So make sure you've got that definition there. Same molecular formula, same structural formula too, but different arrangement of atoms and bonds in space, as in like different three-dimensional conformation of the molecule. Again, pause if you need time at any point. Moving on again. So back to some alkenes then. Now we're going to call it geometric isomerism, but we'll also call it EZ isomerism. It's both things at once. It's the same idea, just with two different names. So I want you to be familiar with both. So we'll keep it relatively simple, and you can see there that we've got dibromobutene. More than that, it's 1,2-dibromobutene, sorry, not butene. So there it is, fine. Now, I already showed you very briefly and without any explanation, like that there's a way of assigning, is it an E or is it a Z? But let's have a think about what E and Z mean, and let's just take a couple of notes at this point. We'll use these two molecules as our simple first examples, like proper examples. So geometric isomerism is a type of stereoisomerism, and as we've said a couple of times already, it's also known as EZ isomerism because we label one isomer as E and the other as Z. All on that will be explained in a second. It's an alkene specific type of isomerism, right? So it's only alkenes where we'll be talking about this, where you've got a pair of molecules that have got the same molecular formula, they even have the same structural formula, but they differ when you look at the arrangement of the atoms in space. Just to confirm, these two definitely do have the same structural formula. Molecular formula is simply C2H2Br2. That's easy, that's the MF, the molecular formula. But even their structural formula, if I just call it the strut F like that, I'd write these both as CHBr double bond CHBr. Right? They're both that, aren't they? CHBr, CHBr with double bond in between. So they have the same structural formula. It's only when you expand them out to display style that you see the difference. Okay. Now, it's specific to alkenes. Why is that? Well, what it is, the CC double bond can't rotate, right? So from this point onwards, with a bit more awareness now, when you look at a skeletal formula in particular, or any structure for that matter, you can imagine that single bonds are able to rotate. Double bonds don't. So what that means is that H and that Br there are sort of locked in position, and then relative to that one CC double bond carbons H and Br, the other CC double bonds carbons H and Br can be locked in the same position. So like the Brs are lined up, like they are in the structure on the left there, the right there, sorry, and the H's too, or they could be kind of alternating, you see? But those are locked, like you can't just twist the CC double bond around and turn one into the other. If you could, then I could just twist the CC double bond and turn the structure on the left into the structure on the right. And if that was a single bond, that would be rotatable and there'd be no tangible difference. But you can't because these CC double bonds can't rotate. I'm not going to go off on a long tangent about bonding in alkenes again. We had a lesson on that, a pretty dense lesson, I'd say, probably, recently. But I'm just going to very briefly explain why CC double bonds can't rotate without going off on a very long tangent. So remember that carbon-to-carbon double bond there has got two types of electron orbital overlap going on in it. You've got the sigma bond, which is the sort of like a single bond type, where you've got those sp3 orbitals, and we're not going to explain those again now, overlapping like short end to short end, right? So you've got the sigma, which is like a little Greek lowercase s bond, which also is S for single, conveniently, but I don't think that's meaningful. And they're overlapping like short end on. And you might imagine that it's a bit like putting two pens like nib to nib and then rolling them in your fingers. And you can roll them on an axis and they still can touch nib to nib while you're rolling them like over like a barrel. So there's a sigma bond that can rotate happily. The other type of bond, though, if I just find another pen color, I don't want to go on for too long about this. Whoops, there we go. The other type of bond, the other type of electron overlap in our double bond, so I'm still getting used to this tablet, is that pi overlap, where you've got a p orbital in both of those double bond carbons, and they're actually overlapping. And that's a kind of like side on to side on. So these elongated p orbitals are overlapping side on. And while this one, if you were to rotate that sigma bond, they're still overlapping. If you were to rotate the carbon-to-carbon double bond, or if it were to just spontaneously rotate, then what would happen is those p orbitals would be like out of alignment with each other, and they wouldn't be overlapping anymore. And basically that means that the bond would break, and nature wouldn't have that happen because it's going to destabilize the system, and that just doesn't happen. So the long and short of it is double bonds just don't rotate. And I gave you a bit of extra explanation as to why that is. It's to do with, to rotate would be to take these two p orbitals, the ones that have drawn green, out of alignment, and they wouldn't be overlapping. The bond would not be there anymore. The bond would break. Just how it is. Anyway, they can't rotate, which leads to this phenomenon of geometric isomerism, also known as EZ. So, what do the E and Z stand for? Now, if we were together in class, I'd get anyone to who maybe spoke a bit of German with a couple of clues to help you, but I'll just throw it up on the slide. It comes from German, all right? Bear in mind that, there's people all over the world who've been doing chemistry for many, many, many years. And in fact, Germany was one of the most important places for chemistry and the chemical industry until very recently. And now it's a more global effort, but some of the greatest chemists ever came out of Germany. Right now, anyway, Entgegen and zusammen, that's opposite or apart basically, and zusammen together. So maybe you can see the logic in E being this one here and Z being the other one there. If Z stands for zusammen, which is together in another language, then you can see here that those two H's and also therefore those two BRs in our example are together, i.e. they're kind of like they're on a separate carbon in the double bond from each other, but they're both on the same, I'm going to call side of the double bond, right? So we're going to have to be careful when we're using sort of descriptive language to talk our way through this. When I say the same side of the double bond in EZ isomerism, I don't mean on the same carbon in the double bond as each other. I mean across the double bond, the two CC carbons, they're like both on the left or on the right if you were to sort of look down it from the down the axis of the CC bond, double bond. Whereas here, this Entgegen, this opposite, suggests because the BRs are not together like they are in the Z isomer, they're like apart. They're on opposite top and bottom, or left and right if you prefer, sides of the structure. Okay, so be aware of that, and hopefully you can see the pattern there. There's not much I can do if you can't see it. You need to just try and get your head around what we're saying here. So this comes about then because, as we said, first of all, because the CC double bond can't rotate. And so in certain conditions, but not this example right here, in certain conditions, that means that there's two possible arrangements. However, there is no EZ isomerism in that structure there. So there we've got just bromoethane. No need to number it because there's only one BR, so it's not relative to anything else. But in bromoethane, there's no EZ isomerism to worry about because you've got a BR, well, because there's two of the same group on the one double bond carbon. So EZ isomerism is exclusive to alkenes, but it's not something that all alkenes exhibit. Okay, it's only when you've got two different groups. But can you see how if I switched out that H like we did before for a BR, then all of a sudden they can be Entgegen, they can be E to each other, or, and we're going back a slide now really by drawing this structure again, those two BRs might be zusammen, they might be together rather than E. So you can hopefully see that it's either E or Z, but it's only when you've got two different groups on both of the carbon to carbon double bond carbons. So a H and a BR and H and a BR or whatever. All right, fine. Moving on again. Now, let's not spend more time on this than we need. Hopefully you can look at that and very quickly say, right, the one on the left is E and the one on the right is Z. Okay? Because you can see that pattern again. But so far, so simple, to be honest with you. So there we're just looking at two of the same thing. Now, I did talk about atomic number earlier, and we will get back onto that. But you can see here that if I just pick two that are the same across the double bond, one on each carbon, then they're Entgegen there, they're apart or opposite. So that's going to be the E isomer. What is that molecule? Well, it's very similar to the examples we had before. It's dichloroethane. More specific still, it's 1,2-dichloroethane. And so the other one must be bracket Z. Oh, sorry, ethene, my bad. It's definitely not ethane, is it? Ethene with an E there, sorry about that. And the other one is the Z isomer. Fine. Now, we've already talked about this, so let's skip that. I've just realised. We're not going to talk about cis and trans, which you can see on that slide, until the end of the lesson. I don't know why that slide's come up twice. Now, sometimes it's not so simple. So I did mention in passing at the start of this presentation something to do with atomic number. Now that structure, 1-bromo but 1N2-ol, bit of a mouthful, that exhibits EZ isomerism. Okay, why does it exhibit EZ isomerism? Well, apart from the fact that I'm telling you it does because the answer's already up on the slide, let's work backwards from that, sort of reverse engineer what we can see here. Each of the double bond carbons has got two different groups attached. It makes no difference whatsoever that one double bond carbon's got two different groups to what the other double bond carbon's got. So before it was just like a H and a BR on both. It didn't have to be that way. But the important thing is there's two different groups from each other on one double bond carbon. And that's the case for both carbons, which means EZ isomerism, or also known remember as geometric isomerism, is a thing. So how on earth would we assign E or Z to that? Well, let's try, as I said, and try and like reverse engineer the answer. Bearing in mind that I mentioned atomic number earlier as well. If this is the Z isomer, then that means that the two groups, although albeit clearly not two of the same group, not like two BRs, are together. All right. So the Z sort of symmetry is like that, where I've got a coloured in circle and a hollow circle. And by comparison with that, the Entgegen, the E isomer, is the one where two groups, now clearly we need to assign those two groups to decide what to put together because it's not two of the same, are in that sort of E pattern rather than the Z pattern. So you can see the difference there, hopefully. Now, we did talk about atomic number. So we're going to use here what we call priority assignment to decide how to decide which one the Z and which one the E is. So we use this prioritization technique. This prioritization technique then, as we said at the beginning, works on atomic number. It doesn't work on MR. So for example, I don't need to weigh like what's the MR of this ethyl group here, and it's 15 plus 14, CH3 plus CH2, and compare that with anything else. It's not as simple as that. All I have to do is compare the atomic number of the atom which is bonded to the carbon-to-carbon double bond. Okay, so we're looking at like which one the priority is on either of the CC double bond carbons, and then looking at those two priority groups across the double bond and assigning them Z or E depending on the pattern that they relate to each other in. So let me just change the pen color again. Let's see what we can do here. So we've already got the answer, but let's try and confirm it. We'll look at the carbon on the left first in the double bond. We've got a C and we've got an O bonded to the double bond carbon on the left hand side. O beats C because oxygen has a greater atomic number. It's element number 8 rather than element number 6. So the O there is going to be our priority atom on the one side, the OH group I should say. Clearly H loses because it's the element number 1, so anything beats it. So Br on the other. So the two priority groups are the bromine atom and the hydroxyl or alcohol functional group. And because they're Z to each other, that's the Z isomer, as you can see. And here it's the same functional group setup. So again, you can see that it must be the other one. O beats C, as it did before. Br beats H. So there you've got that E arrangement, you see? So that's where the logic comes from. Now, once you've got them, we've already said it really, but I'll leave the slide up for a minute in case you want to copy any of these notes down. So once you've assigned priority simply by looking at the atomic number, then you just look at if it's E or Z. And I think when I say whether it's E or Z, I think hopefully you can already see now what the pattern is for being Z or being E. There is something else in case you're looking in the spec, and I'm just going to put this in the middle here. This set of rules that we've just gone through has got a particular name. I don't think you need to worry too much about the name. I think it's more for teachers when it's mentioned in the specification for the course, just so that we know that, oh, right, we better teach all of that then. What we just applied here are what I called the Kahn-Ingold-Prelog rules for naming, okay? There's no point giving you that from the outset because it's more important that you get to grips with what the method is and being able to use it and deploy it accurately. But this system that we've applied here, this idea of prioritization and then looking at it, these are the Kahn-Ingold-Prelog rules for naming, okay? So now you know, and if you see that in the specification, those who look at it, you'll know what it's talking about. It's this. Okay, so pause if you need more time for notes. Let's move on again. Now, it's time for you to get a bit of practice then. There is a separate document that I've attached as a bit of extra in the Google Classroom, which gives you, if you can interpret it, a bit of help on how to name these things. Notice that the two last examples there, the bottom two, have got SH groups in. S is in group 6, just like oxygen is. And if an OH is an alcohol, then an SH group like this is what we call a thiol. Now, there's even more to prioritization in naming, more than you have to do on the course. But I've attached a Word doc which has just got like a sort of picking order list of priorities for naming. If you want to have a go at applying that before I explain it, then have a go at naming all 6 of these as well. But what I want everybody to do, as per the instructions on the slide there, for each of those, just assign them E or Z. And notice that we've got a couple of isomers here, so if one's E, the other's going to be Z. But I want you to use the Carning-Gold-Prelog rules to determine what's what. Okay, so pause the video now, assign them E or Z, and then also if you want to, stretch yourself, have a go at naming them too. I'm going to go through it straight away, so you better pause. Okay, so here we go. Well, we'll assign it E or Z first. This one's not too bad. You've got a carbon, which is obviously higher priority than H because it's 6 versus 1, the atomic number. Br is much higher atomic number than O. So there we go. So there we've got that pattern, which is the Z isomer. Okay. We're going to come back and name them afterwards. Okay, that will do that as extra. Next up, well, it's the same. It's the geometric isomer of the one we've just named, so it must be E. But just to confirm that, Br beats H, O beats C. So yeah, here we've got Entgegen, so that would be the E isomer. Okay, working through it again. Now on the one carbon of the double bond, we've got an O and a C, so it's O. On the other, we've got an N and a C, so which one beats which? Well, nitrogen beats carbon. It's in group 5, that one's in group 4, which means nitrogen in the same period, so N's got one more proton. So again, we've got the Z isomer here. And looking at that one carefully, what have we got? Well, again, the O and the N are the two priority groups on each respective CC double bond carbon. So it follows that it's the E isomer. It's the other one. Next up. Okay, now which is higher priority, S or Cl? Well, the C clearly beats the H, so that's that one up there. S or Cl? I've actually had a complete mind blank, so I'm going to have to look at my periodic table, which is shocking. Well, it's going to be S because it's a whole, and it's going to be Cl. There you go. So there we've got the E isomer. Whoops, sorry about that. And this one here then must be the other one. You've got your two priorities, Cl versus carbon, S versus H. So that's the E isomer as well, because it's actually a different structure to that one if you look carefully. SH and Cl were on the same carbon in one structure and not on the same carbon in the other. So watch out. Right, now I did say about naming, which I've decided we'll do that as a separate video. So if that's everything for now, then good. Because it's a relatively short lesson today, then it's a half-an-hour video, pausing to take notes. It probably took you quite a lot less than an hour. I suggest that everybody has a look at the second video where we'll name those structures from before, and we'll also have a think about this naming priority here. Before that, there is one more little thing on EZ, so we'll do the naming in a separate video, I've decided, and that is about cis and trans isomerism. So you might well come across cis and trans in some wider reading that you might be doing. Cis and trans are somewhat similar to EZ. They also are relating to alkenes, okay? But we won't be using them. Okay, you must be clear on that. So normally cis suggests kind of same, and normally cis lines up with being Z. There is a bit more to it though, you see. So let me just clarify it in case you come across this. Now look at those structures there. Don't be put off by those complicated looking structures. They're actually not that complicated, are they? It's just the carboxylic acid with 18 carbons, right? This is a typical long chain fatty acid. This is the sort of molecule that we call a fatty acid, the sort that comes off a molecule like cooking oil when it breaks down a little bit. So cooking oil, if you're interested, sunflower oil, would be like 3 of these molecules connected through a tiny little skeleton of carbon. We'll look at that in year 13. But look at the double bond here. Look at the carbon-to-carbon double bond. That's cis oleic acid. Can you see how the carbon skeleton goes in that kind of Z arrangement? We would assign that one Z. Yeah, we'd assign it Z because EZ isomerism notation, we're looking at atomic number, aren't we? So you've got a H and a carbon bonded to each of the double bond carbons. So the two C's are Z to each other. So cis here would be Z. And trans there, similar logic, you've got a C and a H on the one. You've got a C and a H on the other. So there you've definitely got the trans type pattern. Okay, so that would be the E. So normally cis is Z and trans is E, but it's not always true because the logic is slightly different. So with cis-trans, normally we're looking for 2 of the same thing. So here we could say those 2 H's are the same as each other, so they're both H, and they're Z to each other. And there, those 2 H's, which are the same as each other, obviously are trans to each other. cis-trans doesn't really work when you've got structures of the sort that we've just worked out here. So you couldn't do cis-trans isomerism notation on that because there's not two of the same thing either side. You get that? And also sometimes it does break down, so it might be that you've got two of the same thing, but because of what's attached, one's E and one's Z, whereas the other would have been trans, the other one would have been cis. So for instance, if I just put the slides back up there, it's all about having two of the same, okay? But we don't use it. Now let me just show you when something might be cis because it's got two of the same group. So here you go, for example, two CH3s. So that would be a cis isomer then, just because it's got two of them. However, it wouldn't also be Z. All right. So what I'm going to need to do is make the CH3 the priority group on one side and not the priority group on the other. So on this side, that is the priority group because C beats H. But on the other side, C gets beaten by Cl, let's say, more protons in its nucleus, larger atomic number. So actually, that would be cis. Let's name it as well. What have we got here? It's butene. It's 2-chloro-butene. So that'd be cis 2-chloro-butene. Whoops, didn't need that bracket. Sorry about that. I needed the bracket there. So cis 2-chloro-butene because the two methyls are together. However, in terms of EZ, priority, the CH3 on the left-hand side, the Cl on the other side. So actually we've got an E-type arrangement there. So that would be E 2-chloro-butene. So cis and Z, E and trans don't always link up. Okay, it's not always that way. We must only ever use EZ, but I wanted you to see cis and trans. Okay, good. So that's it for this lesson. You will have a bit more time. So what I want you to do next is, there's a bit of extension, but it's going to be valuable. Go and listen to what I've got to say about priority and naming structures, and then also we'll go back and we'll name those 6 alkenes that you assigned E and Z to a moment ago. Okay, thanks for that.